And as an example, you can see what the list of problems are there. The septic contaminants from septic seepage is just not nitrogen, there are pathogens, there's phosphorus, potassium, and there are a whole suite of organics that may be causing impact in different aquatic ecosystems. So, looking at low-cost sanitation, we can then think about, and this is where I think demonstrations would be useful to consider, various sorts of waterless and perhaps urine diversion. In essence, generally zero water emission systems as a generic sort of class of alternative sanitation. And as you can see by the arrows, that not only impacts then on the septic seepage, we don't have septic seepage in that situation, it also potentially impacts on the long-term water security, because your groundwater and surface water are intimately and closely linked here. It's a very high water table, and so your source water coming out is really what wasn't the groundwater. If not deliberately taken from the ground, it was not so long ago groundwater, and vice versa. And so zero emission has a lot of sense in these coastal environments where you've got a high water table. And thinking about sea level rise and saltwater intrusion, which is inevitable to some degree in this community, you need to be thinking about, well, what's your long-term water security here for supply of drinking water? And other options and solutions may be using some of the nutrients back directly into agriculture. Instead of closing the loops on that nitrogen, phosphorus, as a bit of a sidebar, phosphorus is a fossil resource. We mine it as rock phosphate at the moment. The largest reservoirs are really in Morocco, where about 77% of the global phosphorus is coming from. We have in Florida US supplies, which may last another 50, 70 years. After that, this country runs out of its currently economically mineable phosphorus for agriculture. So where are we going to get our phosphorus from? Canada, I'm hearing. There's a bit up there. There's a lot more potassium up there than phosphorus.
China.
And China is another big source, but they've got their own interests in their own phosphorus. Thank you very much. Morocco really is going to be holding all the cards. So geopolitically, that's a pretty risky scenario. We already understand the geopolitical side of petroleum reserves being in the Middle East, largely, but not solely. So we're looking at another scenario like that with phosphorus, and not too distant future. And if we think about what are the options here, well, to recover that phosphorus, not putting it out into the oceans. When we release wastewater with our phosphorus and our biosolids ultimately into the sea, that's not recoverable for millions of years, in the sense of the geological cycles before that rock phosphate will reform. So it's out of our vision, okay? So we need to develop systems for recycling phosphorus that don't rely, or don't have in the system, release out into aquatic ecosystems. So recycling phosphorus becomes an essential thing in another 50 to 100 years' time. But because of that infrastructure takes many years to build up, we need to be thinking about that today. So there's another example of looking at this as a whole system. Okay, so the main fertilizers used around the world, nitrogen is required more than phosphorus. So nitrogen fertilizers are very common, and where do they come from? They actually come from Middle East oil that is used as an energy source to fix atmospheric nitrogen. 79% or 8% of the atmosphere in this room is nitrogen gas. Fixing that nitrogen into ammonia and then using that ammonia to fertilize crops. But that's only part of the fertilizer used. Rock phosphate is another fundamental fertilizer used globally in agriculture. So our agriculture can fall apart if we run out of phosphorus that's readily available.
We are already importing 10% of our phosphorus from Morocco right now, because it's becoming too expensive to mine our own.
Exactly. Now, of course, the price of phosphorus went up from $200 a ton to $800 a ton a couple of years ago as people were beginning to realize this problem. Now it's fluctuated back down again. But it's a very worrying concern, as is potassium. So these main nutrients used in agriculture, we totally rely on nitrogen, phosphorus, and potassium. And all of those, of course, are in our, once we eat, we excrete them in our feces and our urine largely the next day. Unless we're growing enormous, that's where they end up. And we need to be thinking about how we effectively close those nutrient loops. So agriculture, including aquaculture, are clearly options, and recovering, of course, the coastal estuarine environment, which is already heavily eutrophied here. How do we harvest those nutrients out to restore those coastal ecosystems? Well, oysters do it naturally, bivalves do it naturally, and so we can make use of those in an aquaculture scenario, which I know the community here is certainly investigating. But more on the background, so there's the rationale for nutrient recycling, if you like. What about energy? Well, as I said at the earlier part of the introduction, organic matter is embedded energy. We burn oil because of the energy in it. It's just organic matter. The same is true of the excreta coming out of us with organic matter is embedded energy. And as you've probably read up there by now, 3 to 7% of the national electricity production, you can see what that costs. It's equivalent to 16 average coal plants, is what we currently use in this country to treat water and wastewater and pump and move it around. Well, funny as it is, yet unutilised, that equivalent amount of energy is actually in the sewer, in the organics, that we're just throwing away at the moment. In fact, using energy to move it and to treat it. So we can work out ways of capturing some of that energy. There's an awful lot there. But when we're thinking of energy and water, there's actually an even bigger part of the picture, which, as you can see, heating hot water in homes uses about 14% of the national electricity production. So if we really want to tackle energy conservation seriously as well, we should be looking at solar thermal and other ways of dealing with heating our water systems. So that's again part of the bigger picture here. We need to be looking at how to deal with energy and the water and the nutrients as they all interact with one another. So next to heating your house and cooling your house, hot water heating is the biggest household consumer of electricity. So now you can see why there are various options to capture that embedded energy which is currently in sewers or in septic tanks. And how do we recover that, and at what scale does it make sense to recover in the community? Can we do that at the household level? Yes, we can, but does it make sense? Or do we do it at clusters of households? And that is why we need to, why in EPA we're developing what we call system analysis tools that help communities think through for your particular physical structure in the sense of the density of homes and housing, where and at what scale does it make sense to capture and recover this energy. So that brings us back to the current paradigm. We have drinking municipal water supplies, treatment, and that's been essential since the early part of the previous century to really reduce cholera and typhoid sorts of outbreaks from various disease-causing bacteria in that case. So we've learned how to control those by treating our drinking water, by both physically removing the particles, by filtration, as well as disinfecting it. That's a robust technology, which is sound, but it's not the only way to deliver drinking water to people in homes. But that's the current paradigm, and then of course the wastewater comes from that. Just some terms so we're clear. Black water is what we refer to, what comes from the toilet itself, which normally in a house is plumbed with all the other drain lines. And those other drain lines we refer to as grey water. So the washing machine, the kitchen sink, the bathtub, that's what we refer to as grey water. So when grey water and black water are mixed, we call that sewerage. And another stream, which is not on this diagram, is yellow water. So if you have a toilet that has a urine diversion function, meaning that the urine stream, with or without flush water, we call it yellow water, goes through a separate pipe, and that's the yellow water component. So, how do we get to this? Well, as I started to say, it was for disease control, is why we were wanting to treat water. But in fact, communities in England and then in the late 1880s in this country, the insurance industry would give you a premium on your house insurance if your community had a community water firefighting system. And so waterworks were actually rolled out not only, but also encouraged because of the insurance, reduce your premium on your house insurance if you were connected to a community firefighting facility, which in this case was done by, and still is today, done largely by water. So in some ways, that's the rationale from a pathogen point of view, disease control, as well as firefighting. And that led us to having excessive amounts of water being delivered, because for firefighting flow, that's what we tend to design our main trunk water systems on, is to make sure we can supply sufficient firefighting flow at individual household fire hydrant release points. Second point here is, for systems view, what's going to be more sustainable? Well, I think I've already set the picture. The current paradigm, as shown here, where we think of residuals as waste, clearly is not sustainable. It's not sustainable from an energy point of view, it's not really sustainable from a nutrient point of view, and from various points of view, even in a water-rich part of the country in general, where there's enough fresh water, we don't think of here as having a water problem, but we have a wastewater problem. And so part of the solution then is dealing with the so-called wastewater. So if we close that loop, we can begin to think about, yes, this part of the country does have a water problem, it's a waste release problem. And on an economic point of view, as you've already debated here, I gather, as a community, about the cost of what a sewering system would be, and the long-term prognosis is that that still is not a very sustainable solution. It's still going to release contaminants into the environment. It's still going to leak, as all sewers do leak. And so, if you look at the bottom line of this graph, back in 2005, but it's as true as it is today, this country is under-investing in the maintenance and repair of the existing water and wastewater services by about $20 billion a year. And that's just continuing to increase. So putting in a sewer is not only a high cost today, it's a long-term cost well into the future. Now, of course, any system is going to cost you something. So the question really then is to look at, over the long term, what is a more or less expensive option for this community. And so it's good that we've got the sewer as a comparison point, because that gives us a reference point. We can cost out what that is today and what it will be over its lifetime of 50 to 100 years. And then we can compare options to that from an economic, but also from a nitrogen and an energy and a water perspective. And those are the tools that we use in the systems analysis approach. I think I've gone through what the likely trends are in the sense of storms, particularly here, but generally there's an aging population, and so none of us are getting any younger. And we're prone to different diseases and different problems as we get older. And so we don't really have a cholera and typhoid problem. I don't know when you last heard of anyone having that disease issue in this country. It's a travelling disease. If you go to some parts of the world, certainly it's a potential. And it's a potential we could reintroduce here, as we've seen in Haiti after the disaster there, and the introduction of the cholera bacteria from some of the aid workers going in there, and because of the lack of sanitation, that could easily spread. So it's not to be taken lightly that these old diseases could be reintroduced. So we need to be aware of that. But as we age, we're actually more prone to different sorts of diseases, and many of these are respiratory. And so what we breathe in through aerosols. So we need to think about, if we have a non-potable or less treated water that might be used in garden irrigation, that might be used in cooling towers and elsewhere, we need to be sure that we're not increasing potential aerosol-related pathogen risks as well, like Legionellosis as an example. Clearly, as we become more globally responsible, we're reducing our carbon footprint. We need to think about reducing greenhouse gases. We know how much methane and nitrous oxides are associated with, along with carbon dioxide usage, with traditional water and wastewater services. We know less about these for some of these alternative systems, so that's something else we're building up an information base in the EPA and elsewhere.